A mutation, any mutation, is a mistake in either DNA synthesis.
So twins are a mistake?
No. Transcription or translation. The size of the mistake, the size of the change that's made, depends, or the seriousness of it certainly depends on the size. So if more than one mistake in a row is made, it's a larger problem than a single mistake. What I mean by that is a point mutation is a change in one single nucleotide. So one base is swapped out for another. So in A, instead of being made in A, when replication occurs, DNA polymerase replaces it with a T. Or RNA polymerase, when transcribing, instead of transcribing a U, transcribes a C. That's a single point mutation. And there are three kinds of point mutations. There are ones that we simply call a substitution. An insertion, and a deletion.
Bless you.
So the three kinds of mutations that we could have are substitutions, insertions, and deletions. So if the original strand read ACT TCA, if a substitution were made, that would be an example of a substitution, where my third nucleotide, rather than being either copied, if it were synthesis, or transcribed as a T, it were copied or transcribed as a C. And insertion is exactly what it sounds like. What do you think that means? So suddenly we have an extra letter. And a deletion sounds like it means what? So now we're one nucleotide short. Which of these do you think are more serious?
Deletion.
Insertion.
Substitution. Is it a trick question?
Not necessarily a trick question.
They're all kind of bad.
They're all kind of bad. One of them may not make a difference at all.
Insertion should be the most. Deletion.
Well, insertion wouldn't matter because it's replication like code, so you could end up with the same thing.
So insertions could be during replication or transcription.
Or sorry, I meant substitution.
So substitution, it could in fact end up as the same thing, and we'll see how in 1 second. Insertions and deletions then end up being the most serious. We class them as a special kind of mutation. Insertions and deletions are what we call frame shift mutations. Now, instead of using nucleotides here, I'm going to give you a sentence composed of 3-letter words. There would be our first codon, right? Our second codon? The fat cat ate the rat. That sentence, does it make sense?
Yeah.
You're all able to read that sentence. Well, there's not. I just made up a sentence that has 3-letter words. So, the fat cat ate the rat. If I were to do something like this and say, delete one of these, we'll start with the deletion.
Oh, it just moved over.
I've just deleted a single letter, right?
Makes sense.
And it shifts the entire way the whole sentence is read. Every single word after the deletion is now incorrect. That seems like a pretty big deal. You guys agree? So that's a deletion. An insertion T-A-T-E-T-H-E-R-A. Insertion. I duplicated one single letter, and what does it make for the rest of my sentence?
Wrong word.
All wrong words, right? After the first word, everything else is wrong. So we call these frame shift mutations because they shift our reading frame. And they're also known as missense mutations. Because they make every single thing that comes thereafter nonsense. The whole sentence is wrong. So of the mutations that we would consider most serious, these are really high up there on the scale of pretty bad things that can happen. As opposed to something like a substitution, if I take my sentence, the fat cat ate the rat, I've substituted one single base there, right? One letter. Now, does the word THT make any sense?
Yeah.
So you automatically, your brain actually does this for you whether or not you realize it. When your brain sees something very close to what it recognizes as a word, it automatically tries to make it a word it knows. Some of you would have read past that error without even noticing it because your brain's trying to help you out when you read. You don't actually read every word on a page. Your brain recognizes patterns. That's how you get faster at reading. This change does not change the meaning of the sentence, right? You still get that there is probably a very fat cat who just ate a rat. That's a substitution, and that's what makes them not quite so serious. Now, what was your bell question on Friday? What is a silent mutation? So we talked about missense mutations. A silent mutation is typically a substitution that doesn't cause a change in the amino acid. So hopefully during codon bingo on Friday, you realized that I could call a codon that coded for an amino acid. So let's say, for example, leucine. You didn't necessarily have to have leucine on your card, or you didn't have to have that codon on your card, did you? Leucine was coded for by many codons. So let's take a look at page 303 of your book. Sky, can you flip to 303? Thanks. So here's my mutation. I have a substitution at the third nucleotide. Translate those into amino acids for me. So you're going to come up with 6 amino acids. So ACA codes for what amino acid? You just give me the first 3 letters. How's that? And CAG codes for? And UCA codes for? ACC codes for what? CAG is going to code for the same thing it coded for above, and so will serine. Even though there was a single mutation, was there a change in the amino acid? So the final protein product remains unchanged. That's why we call it a silent mutation. Because it happened, it's there, it was a mistake, but that's okay. It didn't cause a change in the protein, and the organism in question still completely healthy. So we call them silent. Now these are all simple single point mutations, right? A single change in a nucleotide. Changes. Pretty serious changes. These, instead, are mutations in chromosomes. And these mutations in chromosomes, these are from your book, if you keep flipping a couple pages, I think, if you can't read what's underneath them. One more page for me. One more. There we go. These are in your book on page 308. In these pictures, the rainbow letters A, B, C, D, E, F, those represent genes on a chromosome. So when there's mutations in whole chromosomes, it's a mutation that affects an entire gene rather than one single nucleotide. These are a much, much, much bigger deal. These are the things that cause some pretty serious genetic disorders, things that you would see an individual and recognize that there was something about them that made them very different. An example of one of these, a deletion, I think, on the long arm of the 17th chromosome, so it would be one of these first ones, results in a genetic disorder called cri du cat. Cri du cat is French. It means cry of the cat. And it's a deletion that affects enough genes that it changes the shape of a child's vocal cords. So when the child cries, rather than sounding like a cry, they sound like a small cat meowing, which is why it's called cri du cat. That's kind of a big deal, right? Something much bigger than like a faulty protein product. So that's a deletion where a whole section of genes is deleted. Duplication, you get 2 copies of a whole section of genes. You'd think that's good, right? Having one copy is good, two is better. Having duplications like that cause also some very, very serious genetic disorders. Inversions, you'll notice we had areas of the chromosome switch places. And translocation is when genes move from one chromosome to a whole other chromosome. These mutations are much, much more significant to the organism than any of our other mutations. That, I do believe, takes you to the end of the chapter, my friends. That's everything new from this chapter, knowing that we started with transcription, translation, the genetic code, and all mutations. So that's what your test will be on Thursday.